Welcome to the Deep Dive. If you are joining us today, you are probably the kind of person who loves to peel back the layers of how the world really works.
Absolutely.
You, the learner, want to truly understand complex systems, but without getting completely bogged down by dry academic jargon.
Right. Or feeling like you are trapped in a university lecture hall at 8 in the morning.
Exactly.
Yeah.
You want the big picture, the why and the how, and you want it to actually make sense. And today we have an incredible journey mapped out for you.
We certainly do. We are going to be exploring a region where the Earth itself is in a constant, dramatic, and sometimes violent state of flux.
Yeah, our mission today is to explore the extreme physical geography of Iran. We are looking at a land defined by massive tectonic collisions, ancient vanished mega lakes, and treacherous salt deserts that can literally swallow you whole.
Not to mention the incredibly complex, heavily engineered river systems. It really is a place of absolute mind-bending extremes.
It is. And to really understand a landscape this complex, we had to pull from a remarkably diverse stack of sources.
It is a massive stack. We are looking at a brand new 2025 preprint study focused entirely on Tehran's seismic hazard maps.
Which is fascinating on its own.
Yeah, and we are cross-referencing that with deep geological and seismotectonic reports detailing the formation of the Zagros Mountains, alongside some heavy historical earthquake chronologies.
Plus, we have climate data covering 69 years of wild temperature extremes and detailed environmental analyses of both the Dasht-e-Kavir Desert and the River Karun's intricate water management system. It's a mountain of data, literally and figuratively. But the story it tells is just astounding. In fact, the biggest revelation we are going to share with you today involves a massive prehistoric lake that was until very recently mistaken for a series of deadly earthquake faults.
That is easily one of the most remarkable stories in modern geology.
I still can't wrap my head around it. I mean, that single misinterpretation completely upended modern urban planning for millions of people. And correcting it right now is currently saving immense amounts of money and completely reshaping a major global capital.
It is a perfect example of why understanding the deep past isn't just trivia. It is crucial for our modern world.
Okay, let's unpack this, starting with the literal ground beneath our feet.
That is the only logical place to start, really. Because to understand Iran, to understand its mountains, its deserts, and its hazards, you have to understand its fundamental tectonic reality. The entire region sits squarely on what geologists call the Alpine Himalayan orogenic belt.
Let's pause right there, because orogenic belt sounds like something from a fantasy novel. What does that actually mean for the landscapes you are standing on?
Fair question. Orogeny is just the scientific term for mountain building. An orogenic belt is a massive section of the Earth's crust that has been crumpled and pushed upward by tectonic forces.
So it's a crunch zone.
Exactly, a massive crunch zone. In this case, we are talking about a zone of active, ongoing continental collision. Specifically, you have the immense Arabian plate pushing relentlessly northward right into the Eurasian plate.
And this isn't something that happened millions of years ago and then just stopped, right?
Yeah.
This is an active crime scene.
It is happening as we speak. This immense slow-motion collision is the geological engine driving the creation of the Zagros full-thrust belt.
Full-thrust belt, okay.
Yeah, imagine taking a thick rug on a slippery floor and pushing it from one edge. The rug doesn't just slide across the room. It crumples, it folds, and parts of it thrust upward over other parts.
That's a great visual.
That is exactly what the crust of the Earth is doing there. As the Arabian plate rams into Eurasia, the land folds and thrusts, creating these magnificent, rugged mountain ranges. But that immense pressure also has a devastating dark side. It is the fundamental reason behind Iran's frequent earthquakes.
Yeah, when we talk about this geological engine, the human cost is just devastating. I was looking through the historical chronologies in our sources, and the sheer scale of the tragedies is hard to process. Can we talk about the reality of what happened in the Jilin and Zanjan provinces back in 1990?
It is a sobering reality, and we really have to acknowledge it to understand the stakes of the science here. The June 1990 earthquake in that region was a 7.7 on the Richter scale. It claimed 35,000 lives.
35,000.
Yes. And beyond that horrific death toll, it left 500,000 people completely homeless in a matter of minutes. Entire villages were just erased from the map.
Just reading those numbers makes you stop and take a breath. 500,000 people losing everything overnight. And the historical record shows this isn't an isolated anomaly at all. There was the Tabas earthquake in September 1978.
Yes, that one measured up to a 7.9 magnitude. It leveled the town of Tabas and all the surrounding villages, resulting in 15,000 fatalities.
And then many listeners might actually remember watching the news during the December 2003 Bam earthquake.
That was a highly visible tragedy globally.
It really was. It was a 6.3 magnitude quake that struck the historic city of Bam. Over 2,000 people lost their lives. But on top of the tragic human loss, roughly 60% of the city's historic mud brick buildings were completely destroyed.
Including the Argabam.
Right, we are talking about one of the most beautiful ancient citadel structures in the entire world, a place that had stood for over 2 millennia, just reduced to dust in seconds.
Which is incredibly tragic. But it highlights exactly why scientists, geologists, and engineers are working so tirelessly to map this danger accurately. You cannot stop the Arabian Plate from moving.
No, you can't fight geology.
You really can't. But if you can understand exactly where the resulting stress fractures are, you can prepare. And this is where modern geospatial techniques come into play, specifically Geographic Information Systems, or GIS.
So the sources outline how researchers essentially took earthquake data spanning over a century, from 1900 to 2010, and ran it through these GIS spatial analysis models. But they didn't just dump all this raw historical data into a computer and hit calculate, did they?
No, that would give you a wildly inaccurate picture. Think about it, an earthquake recorded by an early seismograph in 1920 does not have the same instrumental precision as one recorded by a digital, highly calibrated station in 2005.
Right.
So the researchers had to filter and weight the data by accuracy. Older, less precise events, perhaps those derived from historical accounts or rudimentary tools, were categorized differently than modern, highly accurate instrumental readings.
So it's about treating the data with the right level of skepticism. If a report from 1910 says an earthquake happened near this town, it gets a wider margin of error than a 2010 report that gives exact GPS coordinates.
Precisely. By combining this rigorously filtered historical data with detailed maps of known active faults, the GIS software was able to identify 5 major seismogenic zones across Iran.
Paint a picture of these 5 zones for us. Where are the true danger areas?
Sure. Zone 1 is situated up in the northwest, running near the border with Turkey. Then you have Zone 2, which sweeps across the Alborz mountain region and hugs the southern coast of the Caspian Sea.
Okay.
Zone 3 is actually the widest continuous area. It follows a distinct northwest to southeast trend directly along that Zagros folded range we were just discussing. Zone 4 covers the east-central part of the country. And finally, Zone V is tucked up in the northeast.
And when the researchers layered the spatial density maps over these zones, what did they find?
A very clear, chilling correlation. The mapped active fault lines align almost perfectly with the epicenters of historical earthquakes. It essentially proves that these specific crustal faults are the primary seismogenic sources. They are the literal ground zero for the region's seismic violence.
Oh, to really understand how weird and complex this geology can get, the sources zoom us in on a specific city, Bandar Abbas. This is a major port city down south located in the transition zone of the Zagros Mountains. The text mentions it sits right where the Makran accretionary prism meets the Oman Mountains. And I have to be honest, accretionary prism sounds like a weapon from a sci-fi movie.
It really does sound futuristic.
What exactly is that?
To understand it, imagine a snowplow moving forward. As the oceanic crust subducts or dives underneath the continental crust, it acts like that snowplow. It scrapes off massive amounts of marine sediment, mud, and rock from the diving plate, piling it up into a massive wedge-shaped structure. That scraped-up pile is the accretionary prism.
Oh, wow. So Bandar Abbas is sitting right next to this massive geological snowplow pile. And it's also near something called the Manab-Zendan Fault, which the sources describe as a dextral strike-slip fault. Let's translate that for the listener.
A strike-slip fault is when 2 blocks of earth are sliding past each other horizontally. Dextral just means it is a right lateral movement.
So right lateral meaning?
Oh, meaning if you were standing on one side of the fault looking across at the other side, the land on the far side would appear to be moving to your right. Think of 2 massive cars parked tightly next to each other, and one suddenly scrapes forward against the side of the other.
That makes a lot of sense. And this specific fault is crucial because it acts as a major structural boundary between the massive Arabia plate and the smaller Iran microplate. But here's the part that genuinely blew my mind. The ground directly under Bandar Abbas isn't just solid bedrock. The sedimentary cover there, the layers of rock, mud, and scraped-up material, is incredibly thick. We're talking about a layer that is 10 to 15 kilometers deep.
It is an immense amount of material. And because of that massive layer of sediment, the earthquakes here behave very strangely. Take the magnitude 7 Kurgu quake in 1977. Geologists discovered that this earthquake happened entirely within this sedimentary layer rather than deep down in the crystalline bedrock below.
That's wild.
Yeah, they actually classify them uniquely as subsedimentary Zagros-type earthquakes.
How does an earthquake happen inside a pile of sediment? Doesn't there have to be rigid rock snapping to create that kind of energy?
That is where the deep geology of the region gets fascinating. The mechanics of these subsedimentary quakes are heavily influenced by something buried deep below the Proterozoic Hormuz Salt Formation.
Right. I love the analogy the researchers use for this in the sources. They describe an ancient layer of basically massive deposits of salt that can be up to 1,000 meters thick. Think about that. A solid kilometer of salt buried underground.
And salt behaves very differently than normal rock under pressure. Think of that massive, kilometer-thick layer of salt as a giant layer of geological lubricant.
Lubricant.
Because salt is relatively weak and can actually flow and deform when put under the immense heat and pressure of the Earth, it allows the heavy rock layers above it to slide, fold, and detach from the bedrock below.
So the rock layers are basically surfing on a subterranean ocean of pressurized salt.
That is a brilliant way to picture it. And it gets even more dramatic. Because salt is inherently less dense than the heavy sedimentary rock piled on top of it, it desperately wants to float upward. Over millennia, as tectonic pressures squeeze it, this salt pushes up through weak spots, cracks, and faults in the overlying rock. It slowly rises to the surface, creating massive towering structures called salt diapers or salt domes.
It creates a landscape that is just constantly shifting, sliding, and deforming. If you are a city planner in Bandar Abbas, how on earth do you manage the risk in such a volatile area? You can't just guess where the ground is going to turn to jelly.
You absolutely cannot guess. That is why scientists have developed a complex decision support system, or DSS, specifically for this region. This system doesn't just look at one variable, it layers multiple types of highly detailed data. It uses digital elevation models to map the precise topography. It overlays historical seismic records, the exact GPS locations of active faults, and crucially detailed soil classification types.
Let's touch on that because the type of soil dictates how hard the ground will actually shake during a quake, right?
Exactly. It is a phenomenon called site amplification. If you build a house on solid bedrock, the earthquake waves pass through very quickly. But if you build on soft, deep sediment like the kind found around Bandar Abbas, those seismic waves slow down and get trapped in the soft soil, amplifying the shaking dramatically. It's the difference between shaking a brick and shaking a bowl of gelatin.
So the DSS synthesizes all these variables, the faults, the topography, the soil types, to create highly detailed hyperlocal hazard maps. And for Bandar Abbas, the system clearly shows that the areas immediately to the north and east of the city are at an incredibly high risk for severe seismic activity. This isn't just an academic exercise either. This tells planners exactly where it is safe to build residential zones, what engineering standards are required, and where to absolutely avoid putting a hospital or a power plant.
Which is the ultimate goal of all this geographical analysis: practical application that saves lives.
Which brings us to the absolute wild card of our deep dive today. We are moving from the southern coast of Bandar Abbas all the way north to the capital city, Tehran. And this is the story of the new 2025 preprint study. Now, for decades, the paradigm for urban planning in Tehran was based on a terrifying assumption about the city's southern districts. Can you set the stage for what scientists thought was happening there?
To understand the panic, you have to look at Tehran's location. The city sits right at the foothills of the central Alborz Mountains, which is a highly active, heavily folded tectonic zone. For years, regional geologists and hazard models identified several prominent geological scarps in the southern part of the city.
And a scarp is essentially just a very steep bank or a sudden slope in the Earth's surface, right? Like a step in the landscape.
Yes, a sharp change in elevation. These specific scarps were named the North Ray, South Ray, Kar-Izak, and Eshtahard scarps. Because Tehran is in such a seismically active region, geologists logically assumed that these sharp breaks in the landscape were active, potentially deadly fault lines. They looked exactly like places where the Earth had violently shifted vertically.
And the knock-on effect of that assumption was massive. Because of these supposed fault lines, the southern districts of Tehran, places like Ray and Islamshar, which are densely populated and have been rapidly urbanizing, were zoned for extremely high ground motion in the event of an earthquake.
The estimates were severe. We're talking about predictions of 0.40 to 0.70 gram peak ground acceleration for a 24-475-year return period.
Okay, let's translate May 0.70 gram peak ground acceleration for the listener. What does that actually feel like?
Peak ground acceleration, or PGA, measures how hard the Earth accelerates during a quake. 1.0 gram would be an acceleration equal to the force of Earth's gravity. So 0.70 gram means the ground is violently throwing you laterally or vertically with a force equal to 70% of gravity.
That sounds incredibly destructive.
In plain English, it is catastrophic, building leveling shaking. It is the kind of force that snaps concrete pillars and tears infrastructure apart.
So understandably, building codes in southern Tehran were incredibly strict and astronomically expensive because engineers believed they had to design structures to withstand an apocalyptic rupture right under their feet. But then the plot twist.
What's fascinating here is how science corrects itself when multiple disciplines finally talk to each other. Between 2014 and 2025, a wave of new, highly detailed paleoseismological investigations took place. Researchers decided they needed more than just surface-level observations. They brought in heavy equipment, dug deep trenches directly across these supposed fault lines, analyzed the sediment layer by layer, and studied the geomorphology. And they made a stunning, paradigm-shifting discovery.
I still grin every time I read this part of the sources. Those prominent scarps. The terraforming fault lines that dictated decades of urban planning. They are not tectonic faults at all. They are beaches. Ancient dried-up beaches.
It is almost unbelievable, but the data is undeniable. They are the paleo shorelines of a massive, ancient body of water that scientists have dubbed Pamela, the paleo-mega lake of Ray.
Wait, how does an entire community of geologists mistake a beach for an earthquake fault? Aren't those incredibly different geological features?
You would think so. But remember that 10,000 years of wind, erosion, and urban development can disguise a landscape. A sudden drop in elevation created by ancient water carving away the earth can, to a surface-level survey, look identical to a sudden drop in elevation caused by a tectonic plate slipping downward. It wasn't until they dug into the earth to look at the actual composition of the dirt that the illusion shattered.
And Paola was no puddle. The sources say it existed over 10 millennia ago, and it was 1.7 times larger than the modern Caspian Sea.
Which is difficult to conceptualize, honestly.
Right. The numbers are huge. The text says it held nearly 128,000 cubic kilometers of water, sitting at an elevation of 1,010 meters above sea level. What does 128,000 cubic kilometers of water even look like?
To put that in perspective for you, imagine taking the entire state of Texas, every city, every highway, every desert, and submerging it under roughly 600 feet of water. That is the volume we're talking about. It was a true mega lake. The remnants of its shores stretch all the way from the current site of Tehran across the country, reaching as far as Afghanistan.
That is just wild. Now let's talk about the specific evidence because the way they prove this is brilliant. Near the city of Maybad, researchers took deep sedimentary samples right from the face of these supposed fault lines. And instead of finding crushed ground-up rock, which you would expect from tectonic plates grinding together, what did they find?
They found that the soil profile was composed of 90% silt and clay, densely packed with limestone nodules.
And what does silt, clay, and limestone tell a geologist?
It tells them a very clear story about the environment. Silt and clay are incredibly fine particles. They only settle out of the water and accumulate in very specific environments, specifically the low-energy, shallow, calm waters of a lakeshore or a slow-moving delta.
Because fast water would just wash them away.
Exactly. If it were a fast-moving river or a violent tectonic zone, those fine particles would be washed away or pulverized. Furthermore, the limestone nodules form over centuries in exactly that kind of calm, aquatic environment. You simply do not get those delicate formations from the violent shear forces of a strike slip or thrust fault.
But it wasn't just the geologists who figured this out. The sources highlight that archaeologists corroborated the geology, which is just the coolest crossover.
It is. When archaeologists looked at the locations of ancient human settlements in the region, the puzzle pieces fit perfectly together. The ancient city of Hecatopolis in Damgan, a massive historical site, was built right on the shores of one of Pamela's connected satellite lakes.
And they found evidence from the residents of Tepe Hesar, another ancient settlement, proving that those people survived largely on a diet of fish pulled from these exact waters. You don't build a fishing village on a dry earthquake fault.
Exactly. It is a beautiful synthesis of paleoseismology, sedimentology, and human archaeology.
So armed with this revelation that the southern faults were actually just ancient beachfront property scientists had to completely redraw the seismic hazard map of Tehran. This brings us to the core of the 2025 Revised Probabilistic Seismic Hazard Assessment, or PSHA. How did they actually calculate the new map?
Well, they systematically removed these fake faults, the North Ray, South Ray, Karizak, and Eshtahard scarps, from their computer models entirely. They no longer existed as sources of earthquakes. Then they had to apply updated mathematical models, specifically the NGA West 2 ground motion prediction equation.
Let's translate that. What is a ground motion prediction equation?
It's essentially a complex mathematical formula that predicts how hard the ground will shake at a specific location, given an earthquake of a certain size happening at a certain distance. The NGA West 2 models are just the most modern, highly refined versions of these formulas based on massive global databases of recent earthquakes.
And the sources mentioned they ran all of this through a logic tree framework. Is that just an algorithm?
Think of a logic tree as a massive high stakes. Choose your own adventure map for computer probabilities. Because there is always uncertainty in geology, we don't know exactly how fast a fault slips or exactly how deep it goes. A logic tree allows scientists to input multiple different scenarios and assign a probability to each one. The computer then calculates all possible outcomes to give a balanced, highly reliable average of the true hazard.
And the result of running this new lakeshore-aware data through the logic tree was massive for the people living in southern Tehran. The ground motion estimates dropped significantly down to 0.2 to 0.5 G.
Which is a dramatic reduction from the 0.40 to 0.7 of their gram estimates they were working with before.
This is a total game changer. Think about what this means for you if you're a developer, a homeowner, or an urban planner in Tehran today. The study explicitly points out that this revision translates to an 8 to 10% decrease in design-level seismic loading,
which carries immense, tangible financial implications. If you don't have to engineer a building to withstand an apocalyptic 0.70-degree shockwave, you use less steel, less concrete, and less complex dampening systems. The reduction in required retrofitting and structural reinforcement saves approximately 150,000 to 200,000 Iranian rials per square meter of construction.
So for a standard 2,000 square meter commercial or residential building, that is a direct cost savings of 300 to 400 million rials. It proves that accurate geological mapping doesn't just satisfy academic curiosity. It drives massive economic efficiency and completely changes the trajectory of a city's growth.
However, we have to be very careful not to paint an overly rosy picture. We cannot let Tehran entirely off the hook. The ancient lake shorelines in the south are safe from rupturing, yes, but the mountains to the north are a completely different and very terrifying story.
Right. It's like finding out the monster isn't under your bed, but then realizing it's actually in the attic.
Wow.
It's happening in northern Tehran.
While the southern risk was drastically overestimated, the northern threat remains very real and potentially catastrophic. The North Tehran Fault is a massive, verified thrust fault running right along the base of the mountains where the northern suburbs are built. It is capable of generating a 7.4 magnitude earthquake. And to make matters worse, it is physically intersected by another major fault line called the Moshe Fault.
And researchers didn't just guess at the danger here. They dug trenches here too, right?
Yes, paleoseismological trenching. By digging deep into the fault and analyzing the disrupted layers of soil, scientists can essentially read the history of the fault like a barcode. They found evidence of massive violent ruptures in the past, and the data shows that the North Tehran Fault experiences a major rupture roughly every 2,000 years.
And based on the historical timeline, let me guess.
Based on the historical and geological record, we are currently inside that window. The last major event on this fault was approximately 2 millennia ago.
That is deeply unsettling.
It is a stark reality. Northern Tehran remains essentially a tectonic time bomb. It is a vital reminder that while removing false positives from our hazard maps like the Pamela Lake shores is incredibly important for economic development, we must remain hyper-vigilant about the verified threats that still exist.
From the invisible shifting threats beneath the Earth, let's transition to something much more visible but ironically equally difficult to manage: water. We've talked about the ghost of a lake from 10,000 years ago, but Iran's modern water bodies define its climate, its agriculture, and its economy today.
The contrast between the country's northern and southern water bodies is striking, and it dictates the entirely different ways of life in those regions. Let's start in the north with the Caspian Sea. As we noted when comparing it to Pamela, the Caspian is the largest inland body of water in the entire world. It sits in a massive depression about 30 meters below global sea level.
I found a detail in the sources really interesting about the Caspian. Its water level isn't static. It is currently rising by about 15 to 20 centimeters a year, which doesn't sound like much until you realize how vast the surface area is. That is an enormous influx of water altering the coastline year by year.
And beyond the changing coastline, it is an ecologically vital region. It is famous globally, of course, for its sturgeon populations and caviar production, which relies entirely on the specific brackish conditions of that water.
And then you swing all the way down to the south and you hit the Persian Gulf. Totally different vibe. It's incredibly shallow compared to the oceans. The sources note it's only about 36 meters deep on the Iranian side, though it does get deeper as you move along the Iranian coast.
The environment there is punishing. The climate features scorching heat and suffocating thick humidity. And geographically, the seafloor is mostly a muddy bottom covered in calcium carbonate deposits. It is a high-temperature, highly saline environment.
And if we look inland away from the coasts, we can't forget Lake Oromie in the northwest. It's a massive salt lake recognized by UNESCO as a globally significant area. It acts as a vital stopover for millions of migratory birds, though, as the sources allude to, it has faced severe drying and environmental crises in recent years due to climate shifts and damming.
But if we want to talk about the true beating heart of Iran's interior, the lifeblood of its agriculture and power grid, we have to look at its complex river systems. And none is more important or more heavily engineered than the mighty river Karun.
Here's where it gets really interesting. The Karun is Iran's longest and largest river. The stats are staggering. It boasts a massive catchment area of 67,000 square kilometers. It travels over 800 kilometers, originating from the snowmelt high up in the Zagros Mountains, winding its way down through deep gorges and out onto the plains, with a mean annual flow of 575 cubic meters of water per second.
But calling it just a river almost feels inadequate. Today, the Karun is a heavily managed, fiercely contested corridor of power generation, agricultural lifeblood, and unfortunately, industrial waste.
To understand the sheer scale of the engineering happening here, geographers and hydrologists divide the Karun into 3 distinct zones. I want to walk through these because it shows how a single river changes its identity completely based on the topography.
Let's do it. Zone 1 is the lowest section, encompassing the final 360 kilometers stretching from a city called Gatvan down to the Arvan Rud, where it finally meets the Persian Gulf.
This is the flat floodplain. The water here is moving slowly, meandering across the flat earth. Because of that, it is heavily utilized for agricultural irrigation and municipal water supply for the cities built along its banks. But crucially, because it's so flat, there is zero potential for hydroelectric power generation here. You need gravity for that.
Exactly. So then you move upstream to Zone 2, which covers kilometer 360 up to 480. Now the landscape is changing. You are moving out of the plains and into the steep rocky valleys of the Zagros foothills.
But the sources say you can't build massive storage dams here? Why not?
Because the local geology won't support the weight or the water pressure of a massive reservoir. The rock isn't stable enough to hold back billions of gallons of water. However, the river is moving fast enough down these slopes that engineers can build run-of-river power installations. This is where you channel the natural fast flow of the river directly into turbines to spin them without needing to build a massive wall and a lake behind it.
But the true engine of the Karun, the part that powers the nation, is Zone 3. This stretches from 490 kilometers to 670 kilometers upstream deep in the mountains. This is the powerhouse. The text points out that the river drops an astonishing 450 meters in elevation across this single stretch.
That kind of vertical drop is a hydrologist's dream. The topography features deep, incredibly narrow rock valleys that are geologically solid. They are perfect for building high-storage dams.
And Iran has capitalized on this immensely. This zone is home to massive engineering marvels. We are talking about the Karun and Des dams, Karun 1 and the Gadari Landar. The government's stated goal in the sources is staggering. They want to generate 10,000 megawatts of hydropower from this river system over the next 20 years.
But generating power is only one piece of the puzzle. The river is currently the subject of a terrifying high-stakes balancing act managed by the Khuzestan Water and Power Authority, or KWPA. They are engaged in a constant daily battle for optimization.
Let's break down the sides of this battle. On one hand, the KWPA needs to hold water back in those massive reservoirs to spin the turbines and hit that 10,000 megawatt power goal to keep the lights on across the country.
Correct. But on the other hand, down in Zone 1, the government is trying to radically expand agricultural irrigation in the lower plains. They are aiming to increase irrigated land from 280,000 hectares to 480,000 hectares to ensure food security. That requires massive amounts of water to be released from the dams.
And the third, most critical and honestly most depressing variable in this balancing act is the pollution crisis. The scale of the contamination entering the lower Karun is hard to wrap your head around. I want to read this directly from the notes because it's so shocking. Take the city of Alborz, which sits right on the river. You have 1.5 million people living there, and they are discharging roughly 2 cubic meters per second of raw, untreated urban sewage directly into the river system.
2 cubic meters a second. That is a relentless, massive volume of biohazard.
And that's just the human waste. Add to that the chemical fertilizer runoff from the expanding agriculture we just talked about, and the raw industrial wastewater being dumped in from massive sugarcane processing plants and paper pulp factories lining the banks.
Now connect this to the climate context, because this is where the balancing act turns into a crisis. During the summer in this region, temperatures regularly exceed 50 degrees Celsius.
That's 122 degrees Fahrenheit. That is Death Valley level heat.
At those temperatures, evaporation rates off the surface of the river and the reservoirs are incredibly high. Millions of gallons just vanish into the hot air. If the KWPA decides they need more electricity and they hold back too much water behind the dams in Zone 3, the physical volume of water flowing down in the lower plains drops dangerously low.
And what happens when the river flow drops, but the city of Alborz is still dumping 2 cubic meters of sewage into it every single second?
The river essentially dies. Without a sufficient baseline volume of fresh water, what hydrologists call the low flow requirement, to dilute that massive influx of sewage and industrial chemicals, the concentration of toxins skyrockets. The dissolved oxygen levels in the water plummet to zero, massive fish die-offs occur, aquatic life perishes, and the water becomes actively toxic for the hundreds of thousands of people relying on it downstream for washing and farming.
So the KWPA can't just guess when to open the floodgates. They can't just say, well, let's release a bit more water today. If they get it wrong, they either cause rolling blackouts by draining the power reservoirs, or they create a toxic ecological disaster downstream.
Yeah.
How do you solve a problem with that many moving critical parts?
You need data. You need a truly staggering amount of real-time data. The solution currently being implemented is a massive multi-stage decision support system. Remember the DSS we talked about for earthquakes in Bandar Abbas? This is the hydrological equivalent. It involves outfitting the entire 800-kilometer river basin with advanced telemetry sensors.
So they were basically wiring the entire river.
Yeah, literally wiring it. These sensors provide real-time, minute-by-minute updates on water quality, chemical concentrations, flow rates, and meteorological data at dozens of points along the river. But they don't just look at what is happening now. They combine this real-time data with GIS spatial modeling and satellite assessments of the snowpack slowly melting high up in the Zagros Mountains to predict exactly how much water will be entering the system weeks or months from now.
It's basically a supercomputer model trying to predict the future. It has to balance holding water for the 10,000 megawatt power goals, releasing enough water to keep the thirsty sugarcane fields alive, maintaining enough empty volume in the reservoirs for flood control when the heavy spring rains hit, and ensuring that vital baseline flow, so the untreated sewage of 1.5 million people, is diluted enough to keep the river biologically alive.
It is an absolute high-wire act of modern hydrology. And what makes it so precarious is that this hydrologic high-wire act is taking place against the backdrop of some of the most extreme, unpredictable climatic conditions on the planet. Iran's climate is a study in brutal, breathtaking contrasts.
You are not kidding. As I was reading the climate data covering the last 69 years, I couldn't believe these temperatures were recorded in the same country. The geography creates these crazy microclimates. Because the massive Alborz and Zagros mountain ranges act as giant walls, they literally block humid air coming off the Caspian Sea and the Mediterranean from ever reaching the interior of the country.
Yeah.
So you end up with these vast, hyper-arid inner zones that receive almost no rainfall.
Meanwhile, the coastal Caspian region trapped on the other side of the Alborz Mountains receives over 1,000 millimeters of rain a year. Because all that moisture is trapped against the mountains, it creates an incredibly humid semi-tropical environment. It is lush with dense forests, tea plantations, and terraced rice fields. It looks more like Southeast Asia than the Middle East. Conversely, if you travel to the western and northwestern mountainous regions, they endure freezing, brutal winters buried under heavy snow for months.
The temperature records we have really paint the picture of these extremes. Let's look at the heat first. In August 2022, the city of Abadan, down near the Persian Gulf, hit an apocalyptic 53.0 degrees Celsius.
Which is 127.4 degrees Fahrenheit.
Just surviving in that heat is a monumental task. Your body cannot cool itself. Infrastructure literally begins to melt.
Yet contrast that with the city of Ardabil up in the northwest. In January 2018, their weather station recorded a bone-chilling minus 23.0 degrees Celsius or minus 9.4 degrees Fahrenheit. The swing between those two extremes in one country is astonishing.
But beneath these wild, localized extremes, the blizzards and the heat waves, the climate data reveals a quiet, highly concerning trend. Over the last 23 years, researchers analyzing data from consistent, continuous weather stations have found that the national average temperature of Iran has risen by approximately 0.5 degrees Celsius.
Half a degree might not sound like much to the casual listener. You might not notice if your living room went from 70 to 70.5 degrees. But in a delicate, hyper-stressed environmental system, it is massive. When you are already pushing 53 degrees in the summer and your river systems are struggling with intense evaporation and heavy pollution, that half degree acts as a threat multiplier. It accelerates evaporation, dries out the soil faster, and puts immense strain on the power grid as people run air conditioning much longer.
And nowhere is the hostility of the Iranian climate more apparent or more deadly than in the Dasht-e Kavir.
The Great Salt Desert. It is a vast, surreal, almost alien expanse stretching across the central plateau of Iran. It covers an astonishing 77,600 square kilometers, measuring roughly 800 kilometers long by 320 kilometers wide.
I want to try to describe what this looks like based on the sources. Imagine standing in the middle of it. You are not standing on sand dunes like the Sahara. You are essentially standing on the floor of an ancient dried-up ocean. When that ocean evaporated millions of years ago, the water left, but the salt stayed. It left behind layers of salt that are 6 to 7 kilometers thick in some places.
Over deep geological time, wind blew and dust and flash floods washed in mud and sediment, slowly burying that massive ocean of salt. But just like we talked about with the sub-sedimentary earthquakes in Bandar Abbas, salt is inherently less dense than mud and rock. It is buoyant.
So over millions of years, that buried ocean of salt pushed its way back up through the heavy mud crust, creating these massive bubbling formations. The sources say there are roughly 50 massive salt domes that have broken the surface across the desert. It must look like a landscape on Mars.
It is incredibly desolate. But the true danger of the Dasht-e Kavir isn't just the 50-degree heat or the lack of water or the isolation. It's a specific geological phenomenon the locals call the sharbe.
This part terrified me. Explain the sharbe.
To the naked eye, a sharbe looks perfectly safe. The surface looks like solid, rigid, baked earth, a hard, flat crust of dried salt and mud. It looks like you could easily drive a truck across it, but that crust might only be a few inches thick.
And beneath it?
Beneath that deceptively thin crust lies a deep hidden layer of smooth, oily, incredibly viscous mud. It is a mixture of water and fine sediment trapped beneath the salt. If you walk or ride a camel or drive a vehicle onto the sharbe, your weight shatters the brittle crust and you plunge instantly into the muck.
And you can't just wade out of it.
No, you really can't. Because of its intense density and stickiness, it acts exactly like quicksand, but arguably worse because of the chemical composition of the salt mud. It creates a vacuum suction effect. Falling in is often a literal death trap. Escaping without immediate external help is nearly impossible. Many travelers and vehicles have simply vanished into them.
It's terrifying. A desert that physically swallows you. And yet, humanity and nature has always found a way to survive and even thrive in these extremes. That's the resilience of life. Despite the heat, the lack of water, and the deadly charbol, the Dasht-e Kavir wasn't an empty void. It was actually a major, heavily trafficked thoroughfare for the ancient Silk Road.
Which speaks volumes to the ingenuity of the ancient traders. You can still see the remnants of their survival strategies today. They built ancient caravanserais, like the beautifully preserved Miranjab caravanserai. These were essentially massive fortified rest stops and oases spaced a day's journey apart, providing safe harbor and water for the traders crossing the void.
They navigated their caravans past legendary, treacherous areas of the desert, like the Rigi Jen. The sources translate that ominously as the dune of the Jinn or the spirits, because the shifting sands and remote, seemingly cursed landscape made people believe it was literally haunted by demons.
And while it might not be haunted by jinn, the wildlife that actually lives out there is just as resilient and almost as elusive. Out in this barren, blistering saltscape, you can find Persian onagers, which are these incredibly tough, endangered wild donkeys that can survive on almost no water.
alongside elusive sandcats, desert wolves, and even the magnificent Persian leopard hunting in the isolated rocky outcrops. Finding a leopard in a salt desert just completely shatters your preconceived notions of where these animals live.
Which brings us to a broader appreciation of Iran's unique flora and fauna. The biodiversity is shaped directly by these intense geographical boundaries we have been discussing all day. Up in the sheer, freezing cliffs of the Alborz Mountains, you have the spectacular red goats, famous for their long, sweeping spiral horns. Historically, the country was also home to the legendary Persian lion, a majestic animal that served as a symbol of the empire for millennia, and the massive Caspian tiger in the northern forests. Though sadly, as the sources note, both have been hunted, marginalized, and essentially driven to extinction over the last century.
But the botanical resilience of the region is beautiful, and it left a massive mark on human culture. The ancient Persians were master gardeners. They figured out how to cultivate vibrant life out of arid rock and intense heat. The sources mention writings from early European travelers like the French jeweler Jean Chardin in the 17th century, who traveled through Persia and were absolutely mesmerized by Persian roses.
He documented seeing botanical marvels that European gardeners couldn't fathom at the time. He described massive bushes that grew tricolored roses, yellow, white, and red blossoms, all flowering simultaneously on a single branch.
And of course, the tulips. Most people associate tulips with Holland, but long before tulips became a massive financial mania in Europe, they grew wild in the harsh, rocky Iranian mountains. They were cultivated and revered as a sacred symbol of royal majesty by the ancient Medes and Persians thousands of years ago.
The diversity of life here, from the microscopic organisms thriving in the mud of the Caspian Sea, to the leopards stalking the Dashta Kavir, to the ancient roses, is a direct, vibrant result of the incredible turbulent geography we've been uncovering.
It really is. Every plant, every animal, and every city is a reaction to the shifting plates and the scarce water. And that brings us to the end of our journey today. We have covered an astonishing landscape of contrasts, and I feel like we've only just scratched the surface. We started with the violent tectonic clashes of the Zagros Mountains, learning how the Arabian Plate is crumpling the Earth and how the sliding subterranean salt diapirs of Bandar Abbas create unpredictable subsedimentary earthquakes.
It's been an incredible deep dive.
We unravel the incredible geological mystery of Tehran, where the ghost of a 10,000-year-old mega lake named Pamela pretended to be a deadly earthquake fault, and how discovering ancient beach silt is currently changing the shape and the cost of modern urban planning. We navigated the heavily engineered, fiercely contested, and tragically polluted waters of the River Karun, looking at the massive supercomputer models trying to balance power, agriculture, and sheer survival. Finally, we stepped out onto lethal salt traps, the quicksand of the Sharba, and the 53-degree heat of the Dashti Kavir.
Quite the journey.
So what does this all mean? For you, the learner, the takeaway is profound. Understanding a landscape's deep ancient past is the absolute only way we can possibly survive its future. You cannot plan a resilient city, you cannot manage a complex river system, and you certainly cannot cross a desert without knowing exactly what the earth beneath your feet has been doing for the last million years.
And that deep time perspective, looking at how drastically the Earth can change, leaves us with a critical, perhaps deeply unsettling question, if we connect this to the bigger picture. As climate change drives temperatures incrementally higher across the globe, increasing evaporation rates, altering ancient water cycles, and pushing the very limits of human and ecological endurance, will the sophisticated multi-million-dollar computer models and telemetry networks being built today to manage vital rivers like the Karun be enough to combat the unpredictable compounding extremes of tomorrow? Or, centuries from now, will humanity be forced to abandon these increasingly hostile, hyper-arid regions, entirely leaving behind our massive concrete dams and sprawling dry cities as new ruins, waiting for future geologists to misinterpret?
A chilling but absolutely necessary thought to leave you with as you go about your day. Thank you for joining us on this deep dive. Keep questioning the world beneath your feet, and we will see you next time.